Hi, in this video, I'm going to be solving this Putnam competition problem. It's from 1985, question B1. And the reason why I choose this like totally ancient competition from 1985, because that was my year. That was the year I took the Putnam. And I was at Purdue. I did well in the competition. I don't remember which question I got or anything like that. But I did not do well enough to get any kind of national prize, but I did get the best score at Purdue University, so I did get a prize from the math department at Purdue. So, Putnam 1985 question B1. Let K be the smallest positive integers with the following property. There are distinct integers M1, M2, M3, M4, M5, such that the polynomial P of X is equal to X minus M1 times, and then M2, M3, M4, M5, has exactly K non-zero coefficients. Find with proof a set of integers M1, M2, M3, M4, M5 for which this minimum K is achieved. All right, one tricky part about this question is that understanding the question itself is hard. It's hard to follow what this question is asking. So let's go slow. There's a K of some sort. It's easier if we concentrate on this part first. We have this polynomial. It's a fifth degree polynomial. It has 5 distinct zeros because they have to be distinct. There are 5 distinct zeros that are integers, M1, M2, M3, M4, M5. And they multiply out into a fifth degree polynomial. So x to the fifth plus c4, x to the fourth plus c3, x to the third plus all the way down to the constants. So if you multiply out, you have a polynomial. And because all the m's are integers, then all the coefficients are integers as well. And what this says, it has k non-zero coefficients. So some of these will be 0, and this one will be a 1 for sure. And these could be 0. And they're saying that there are k non-zero coefficients. And then we're looking for the k that is the smallest minimum k. So, in other words, what they're asking is find a set of integers m1 through m5 for which you have the smallest number of non-zero coefficients. Right? If you multiply normally, chances are all 5 will be non-zero. And we want a minimum number of non-zero coefficients. We want to multiply it out so that certain things cancel out, right? So that you have several zero coefficients in there, the rest are non-zero, and they're asking what's the smallest k number of non-zero coefficients. So basically what this question says is find the smallest number of non-zero coefficients that polynomial P of X can have. Given that P of X has 5 distinct integer zeros. And of course, it's a Putnam problem. They didn't have to say with proof, but they did. All right, first let's strategize. Normally, when you have these little binomials, x minus m sub I, and you multiply 5 of them together, you end up with an x to the fifth followed by 5 other terms, so a total of 6 non-zero coefficients. That's kind of what could happen, right? It could have all the way up to 6 non-zero coefficients. Or if you want less than that, then you want it to kind of like cancel each other out in such a way that the when you expand the multiplication, some of them cancel, and you have fewer than 6 non-zero coefficients. Well, working with 5 coefficients or 6 coefficients kind of hard. Let's think about something simple. What about if you have two factors, then you could have x minus m1 times x minus m2, and this one could be three non-zero coefficients, right? But there are cases where it's not three, because if you think in terms of difference of squares, if you think in terms of x minus a times x plus a, then you get x squared minus a squared, and that one only has two non-zero coefficients, not three. So we've reduced it down. And the reason why it works is if you multiply this out, you get x squared minus m1 plus m2, right? This sum here is 0 if the m1, m2 cancel. So if with two factors, I can use x squared minus a squared. What if I increase it to cubed? If I do x cubed minus a cubed, this factors into x minus a times x squared plus ax plus a squared. And this does not factor. So this shortcut here only gives me 1 0, not three distinct zeros. Right? I want up here, it's a fifth degree polynomial. I want 5 distinct zeros. So third degree polynomial, I kind of want 3 distinct zeros, not 1. So for x cubed, it doesn't work that way. X fourth minus a to the fourth factors into x squared minus a squared times x squared plus a squared. And this first one factors, but this one doesn't factor either. So that's no good. If I try to do this same trick with a fourth degree polynomial, I end up with just 2 distinct zeros, not 4. So it seems like I have to stop here. If I go back to this factoring into 5 zeros, and I think, okay, 2 of them, I can use this difference of squares formula for 2 of them, and that leaves a last one. So for example, I can do like x squared minus 1 times x squared minus 4. That gets me x minus 1 times x plus 1 on the first factor, and x minus 2 times x plus 2 for the second factor. And then I have a last one, x minus m5 here. Right? If I distribute this out, I'll get 3 terms. X fourth minus x squared minus 4x squared plus 4. This means I have 3 non-zero coefficients for a fourth degree polynomial. So that's kind of good. And now I need fifth, and I'm gonna distribute and get x to the fifth minus 5x cubed plus 4x, and then I distribute. Oh wait, once I get here, I realize, wait, what if I just stop right there? What if I set m5 equal to 0, right? Then I have 3 non-zero coefficients for a fifth degree polynomial with 5 distinct zeros. I have the 1, negative 1, 2, negative 2, and a 0. And that makes sense. In math, a lot of times when you look for some kind of minimum or maximum, some kind of symmetry tend to get you there. Okay, so this is symmetric. Negative 1, 1, negative 2, 2, and a 0 right in the middle. It seems to be the one. So if I stop here, it's not really a solution. I'm just boxing it up because I'm happy. If I stop here, I have 3 non-zero coefficients for a fifth degree polynomial with 5 distinct zeros. This is great. So I need to prove that this is the minimum. Is k equals 3? Is the minimum number 3? Can I have 2? Or k equals 1? Well, my polynomial has to be leading with x to the fifth. So can k equals 1? K equals 1 means I only have this. No, this polynomial does not have 5 distinct zeros. It only has 1 0 and that's x equals 0. So no, k cannot be 1. Can it be 2? If it's 2, then that means we're looking at p of x is equal to x to the 5th plus some other c. One more term, just it. C I x to the ith. That's it. Cannot have another term. Well, what are the zeros of this? P of x is equal to 0 means x to the 5th plus ci x to the ith is equal to 0, where I is less than 5. Then I can factor out the ith. I have x to the 5 minus I plus c sub I is equal to 0. And that means this is 0, x equals 0. And since I want distinct, then that means I has to be equal to 1, right? If I is more than 1, then that's a 0 with multiplicities. Right? I'm looking for distinct zeros. They cannot have multiplicities, so it can only be 1. So if I is equal to 1, then that means I have x to the 4th plus c sub 1 is equal to 0, meaning x to the 4th is equal to negative c sub 1. And that means x is equal to plus or minus the 4th root of negative c sub 1. This could be a real number. C sub 1 could be a negative number, so minus c sub 1 is going to be positive. 4th root is going to be a real number, and plus and minus. So in terms of being a real number or an integer, it's fine. The problem is this is only 2 zeros of multiplicity to each. So I have 1 0 here and 2 more zeros here. I only have 3 distinct zeros. I don't have 5 distinct zeros. Therefore, it looks like k cannot be equal to 2. But I do have k equals to 3 here, so the minimum has to be 3. So that's my answer, and I can rewrite this proof. This was my strategizing, but I actually have arrived with a complete proof right here on this screen. So let's just rewrite the whole thing as a clean proof. All right, let's go back at the beginning, clean out everything, and now write the proof. Let m1 equals 1, m2 equals negative 1. So these are the m1, m2, m3, m4, and 5 that we found when we were strategizing. So let's just let them be those numbers. Then p of x is equal to, plug in all the m's, multiply the first 2 factors together, the 3rd and 4th factor together, and then x down here. And combine like terms and distribute that x on the inside, then I get x to the 5th. These together makes 5, so minus 5x squared times x on the outside is x cubed, and then minus 4x has 5 distinct zeros and 3 non-zero coefficients. So that means k is at most 3 because we found an example of 3. Also, this may have been obvious, but because the product of the x minus m sub I will result in a leading coefficient, or will result in a leading term of x to the 5th, then that means k is greater than or equal to 1. So it's not going to be 0. So we prove k equals 1 and k equals 2 are not possible. If k equals 1, then that means it can only have one term, and that term has to be the x5th because that's the term we know. And that does not have 5 distinct zeros, and therefore k is not equal to 1. How about k equals 2? Then it has to be equal to x to the 5th plus just one more term, right? Just one more non-zero term. We don't know where it is, so we call it c sub I. Or for some I, we don't know what, but we know it's less than 5 because this one is the one term already, and we're looking for 2 terms. And it could be between 0 and 5. Well, but in that case, p of x is going to be, I can factor out the x to the power I. So that means x equal to 0 from this factor is a 0, but to have no multiplicity, or to have multiplicity 1, it means I has to be equal to 1. So that means p of x is equal to x by itself times x to the 4th plus c sub 1. And to find 0, I go x to the 4th plus c sub 1 is equal to 0, and x equal to plus or minus 4th root of negative c sub 1. And therefore, it only has 3 distinct zeros. It has 0, has 4th root of negative c sub 1, and has a negative 4th root of negative c sub 1. And therefore, k cannot be 2 either. Therefore, k is equal to 3 with these kind of m's, or in general, m1 is equal to some k, m2 is equal to the opposite of it, m3 is equal to some l, and m4 is equal to the opposite of it, and m5 equals 0, where k and l are not equal. And that's the answer. I had fun. Hope you have fun too. Like, share, and subscribe for more contents, and thanks for watching. Bye.